With Gaussian elimination, that's what we're going to talk about now. Gaussian elimination. We can use these matrices. We can use one row to either, and we use the word eliminate, okay, to when you get your matrix in reduced row echelon form, you have eliminated the rows. To eliminate means, well, again, you have leading ones, you have ones on the principal diagonal, zeros below the principal diagonal. So in order for us to eliminate these rows, we can use them against each other. So for example, I can take row number 2, subtract it from row number 1, or vice versa. Or I can multiply one of these rows by some other number, and then that row, whose values have now become multiples of some other number, I can subtract from the first row. This one shouldn't be difficult to do. So for example, just again, for notational convenience, I'm going to lose that 10 to the power 4. And I hope you're okay with that. I'm just going to lose that because, you know, the simpler the notation, the easier it will be for us to keep track of what's going on. And I'm going to lose these parentheses, really get all that clutter out of the way. So again, I want this to be a leading one. And you know what? Just to simplify this so we don't spend too much time, I'm going to reorder these. And that's perfectly fine. That's within Gaussian elimination, you can swap rows. Okay. Anyway, what I've done is I've now swapped the rows. In fact, to denote this, we would say this. R sub 2, and then a right arrow, R sub 1. That means R2 has been replaced with R1. Now, in your opinion, how can I get this to be reduced? Assume this was 2, this was 1, and this was 1 and 1. What would we have to do to reduce this, to eliminate this row? Well, I would say we would subtract row 2 from row 1. So the difference of this row and that row, and then the result of that difference, I would put back into row 1. Let me show you what I mean. So what I'm going to do is I'm going to subtract row 2 from row 1. And the order is important, right? Because if I subtract 200 minus 100, I'll get a positive number, whereas I'll get a negative number the other way around. So I'm going to subtract row 2 from row 1. And then I'm going to take this evaluation, this result, and replace it with row 1. So I will get something that looks like this. This becomes 100. So 200 minus 100 gives me 100. 100 minus 100, that's just going to give me 0. And then 4,000 minus 3,000, that's going to give me 1,000. There we go. So I have 100 up here. Now I need to get this to be a 0. Okay. We're doing Gaussian elimination. Now let's see how I can get rid of that. I can subtract, 100 minus 100. And so basically this, I will subtract this row from that row, and then the result, I will plug it inside row 1. But if I subtract this from that, I'm going to get a negative 2,000. I don't want negative 2,000. So I'll do row 1 minus row 2. So I'm going to go row 1 minus row 2. And then whatever that evaluates to, I'm going to plug that into row 1. So we will get something that looks like this. Okay. 100 minus 100, that's just 0. 100 minus 100, that will stay 100. And then 3,000 minus 1,000, that gives us 2,000. Look at that. Now we have upper triangle. The last thing I need to do is get these to be ones. And what I will do is I will multiply this by 1 over 100. So I'll cancel them out. So to denote that step, I'm going to say that I will multiply all the numbers on row 1 with 1 over 100. And then I'm going to replace row 1 with the result of this calculation. Right, arrow. So that will do what? It will give me 100 over 100. 100 over 100, that's just 1. 0 over 100, that's just 0. And then 1,000 over 100 is just 10. And then I'm going to do the same thing for row number 2. So I'm going to copy this bit. Okay. I'm going to do the same thing for row number 2. Okay. Multiply these values with 1 over 100. And then this is what's going to happen. So 0 over 100, that's just going to be 0. That's going to be 1. And then 2,000 over 100 is going to be 20. And of course, I hope you can see the solution. We've managed to do it. If I put back the times 10 to the power 4, well, we'll get this matrix, this one, sorry, but 10 to the power 4 times 10 to the power 4 times 10 to the power 4. And this is exactly what we had seen in our last session. Right? So what is this? If we plug in these values back into the inequalities we had, this would give us, or after we turn the equalities into equations, we would get 1x plus 0y equals 10 times 10 to the power 4, which is 10 million. And then for the one below, this would become 0x, 1y, 20 times 10 to the power 4. And of course, if we get rid of these zeros, I'm only putting the leading one just so you can see how I'm where I'm plugging these numbers. But in algebra, of course, we don't actually put 1. We don't put the coefficient 1, because that's implied it's there. So the 1 goes away. 0y, that's just, well, that's nothing. That goes away. Here, down here, 0x. So the x goes away. And then 1y, we don't actually need to put the y. We don't need to put the 1. Well, and there we go. That's exactly what we had. This was the point on the feasible region. So we have now seen 2 ways of solving our system of inequalities. One was with classical algebra, and now we've used Gaussian elimination from linear algebra. Now, in my opinion, this is still time-consuming, right? Would you say this is simpler than the algebraic manipulation we saw in our last session, or easier? So Gaussian elimination versus classical algebra. Which one do you think is easier? Laura says same. I suppose. I would say, however, if you're doing multiple inequalities, your Gaussian will be more will be a lot faster. Richard says more organized. I agree, because you don't have to move things to the left, to the right. But yeah, I think with some practice, you might find Gaussian elimination. Furthermore, here's another thing. You probably won't do this by hand in real life. Like if you have an actual LP problem and you have to solve system of equations, you're not going to do this by hand. That would be ridiculous, right? You have calculators. Now, the calculators to which I'm referring are CAS, Computer Algebra System. You know, like Texas Instruments makes them. You would plug in your, you would type in your equation, then say solve for x, solve for y, and you will get the roots. Or you could, but if you have like many constraints, a CAS system is not going to be useful. So you want to use something like Matlab or numpy to solve many system of equations. So in the real world, Gaussian elimination, or at least LU decomposition, which we'll get to, is going to be far more efficient approach than classical algebra. And exactly, yes, you do need to plan a plan of attack, but you have to sit down and think through it. Whereas with technologies like Matlab and libraries like NumPy, you just write a line of code and you have the solution. Okay. But I hope you now see what we have done. You now understand Gaussian elimination.